Hello, Year 13. This is the second part of the video. Hopefully this time we won't be interrupted by elephants or Mr. Mumbo walking through the classroom. Anyway, here we go. So last time we had a car going around a bank track. Well, what I'm going to do now is I'm going to have a car going on a flat track. We're now going to put it on a bank track. Anybody you as a spudding racing driver, you should know that they have bank track and they want the cars to go really fast. Well, I'm going to show you the physics behind why. So first of all, going back to year 12 work. If you've got the car here, again, you've got your mg weight acting down. Then this time they got the support force N1 and N2 and decided to change the name from an S, or the letter from an S to an N. I don't know why, but there you go. The book decided to do it. And this is the picture you'll find exactly in your book, and you'll find it under 2.3. Now, first of all, analysing this, you go to resolve components in a vertical direction. Therefore, the component going up there is going to be N1 cos theta. This one is going to be N2 cos, if I can write properly, theta. Now, in that case then, if I go up and down, I know the total force is acting up is going to be N1 cos theta plus N2 cos theta. That must equal everything going down, which is going to be mg. And that's my first equation. Then, on the second equation, I know this force going inwards is going to provide a centripetal force, and that must be my F equals mv squared over r. Well, I know that one acting this way is going to be N1 sine theta, and that one acting that way is going to be N2 sine theta. Therefore, you should get the drift now, the total force going that way is going to be N1 sine theta plus your N2 sine theta. Come back, pen, always be given. That must then equal to your mv squared over r. Now, the next thing I'm going to do is I'm going to draw a black line. We don't want it. Is I'm going to take that equation there, the N1 sine theta, and I was going to rearrange it a bit before I did that. As I'm going to take the sine theta out and do what I wanted to do is take the sine theta over here, sine theta, and then in my bracket it's going to have N1 plus my N2. That must be equal to my mv squared over r. But I'm going to divide it by this equation over here, which is going to be cos theta N1 plus N2, and divide that by what that equals to is going to be your mg. And this is where the mathematics gets very exciting. Contain yourself. When the N1 and N2 cancel out there, and all our budding mathematicians here know that sine divided by cosine is going to be equal to tan theta. I'll take this one, the m's cancel, and therefore it gives you v squared over rg. Now, what it gives an interesting thing there is the fact that the forces going around involved is to form circular motion. There's no m in here at all. There's no mass. But what this is presuming, there's no friction. Now, the friction should be, well, the car was going out that way. Wouldn't the friction act in the opposite direction? Well, it's taking the point that the car's not moving up or down at all, and it's not moving up and down at all. There's no friction. Therefore, this equation holds true. Now, if you go down to old racing tracks, you'll see they curve like that. And the reason they curve like that, trying to find a wonderful pen in red, is because if you look at the angle here, theta, and look at the angle here, theta, you see theta starting to increase. Well, what they're doing is making tan theta bigger, which means then you can go a faster speed. Obviously, it raises increase as well, but you can have a much larger velocity. It means that as you go to the bank track, you got much, much higher velocity. And they use this to Manchester Velodrome as well. Now, the next wheel example you have is all about the Big Dipper, and you'll find this one on your 2.4. Now, for some reason, I've used SpongeBob SquarePants for better reasons known to myself, not. Here he is going around in a Big Dipper, and you've been in a roller coaster, you should notice that you feel very much heavier on the bottom. Well, there's a simple reason for that. Is the weight acts down that way, and then your support force acts up. And the book uses an S again. Exactly the same way that we've done before. We're modeling this on circular motion, where the center of the circle R is going to be just there. Now, again, using equation F equals mv squared over R. This time I know that the resultant force acts inwards, so this way now is going to be the positive. Therefore, we want it to be S minus mg is equal to mv squared over R. Therefore, now, if you rearrange the equation, the support force S equals mg plus your mv squared over R. Now, if it wasn't going around anywhere, and just on the stationary point, wouldn't S equal mg, straightforward in the vertical plane? Can you see this is the extra force, the support force, and this basically makes you feel heavier. And if you make the velocity bigger and bigger and bigger, you're making that extra factor bigger and bigger. Hence, when you go down like a big one and go whee all the way down, you'll fall very, very heavy. Now, going across then, the lowest one I'm going to show you here, they use this in Big Ape. It's all very exciting. Big Ape, go Ape. God, I can't get words in here. And what they'd have is like a tree trunk just like this. And they strap people on it. And the length of the cable is, I'm going to say L. They first of all hold you up with the force here. Then they let go and go whee, all the way go down like that. And yes, you're smiling brightly at the bottom. Which means then also this is going to have length L like that. Okay? Now, what they can ask is for you to work out the velocity at the bottom, which is dead easy. Getting back to my black pen. At the bottom here, I've got kinetic energy. That's still a blue pen, never mind. Which I'm going to represent as EK. And at the top, I'm going to say it has potential energy. But the loss in your potential energy is going to equal to your gain in kinetic energy. We've done this before, haven't we? Therefore, isn't that going to be mgh? At the bottom, isn't the kinetic energy going to be half mv squared? But this time, isn't the height is going to be above that going to be mgl, where L is going to be the length of your rope, or your cord, or whatever you got. That then equals a half mv squared. And amazing enough, those cancel. Therefore, isn't v squared then equal to 2gl? And therefore, v equals root 2gl. And you met that equation before, but rather than having L, we had an R. Now, when we're at that bottom point there, this is where it gets really exciting, is you've got the mg acting down, which is the weight of the character, and you then got tension T acting up. In other words then, for centripetal force must be T minus mg must be now equal to mv squared over R. But this time the R, isn't it going to be your L? Therefore you have T minus mg is then equal to mv squared over L. And this is where this gets very exciting. What you can do now is, hey, oh, I know what v squared is. Therefore, T minus mg suddenly equals to 2gl over L. Last, I've missed off an m. But you knew that. I'll try that again. I'll try again. It's going to be m multiplied by 2gl over L. Okay, and all I'm doing is taking v squared in here, and I'm taking that value of going to be 2gl. Now, look what happens. Bang, bang. The L's cancel there straight away. And now what I can do is rewrite it as T minus mg is then equal to 2mg. And now if you rearrange it, T is actually equal to 3mg. And the interesting part from that, when they're designing this, what they can do is work out the maximum tension at the bottom part there. And they had to make sure that cord, rope, whatever you're using, must be able to take 3mg. And interestingly, it's not independent of the L. What it's dependent on is that mass. If you've got a bigger mass, you need a bigger T. And that's why all of these literally has it's got a maximum weight limit to it. Now, when you come back, I've just got an email saying you're going to come back tomorrow, but I don't teach you tomorrow, and I'll see you on Monday. Aren't you excited about coming back? I'll start showing you, and I promised Charlie about this. This is basically a pair of Union Jack underpants going round and round, all very exciting. And what I do is start doing the physics behind that, and then, which you know Daniel Vincent's very excited about, we're going to finish off Loop the Loop. Anyway, hope you enjoyed that video. Enjoy your weekend. I'll see you Monday. All keen to start all over again. Bye-bye for now.